turn this slide down a little bit. Okay, so first of all, I'd like to maybe introduce myself. So I'm actually professor, this is my title, Professor of Math, 100%, Statistics, 0%, and Computer Science, 0%. So what this means is that mathematics pays my salary. Through statistics, I get access to interesting data, and students are willing to look at them. And through computer science, I get occasionally free lunch. So let me start. I like to kind of partly do this as an advertisement to statistics, because I think some of you may not think of statistics as a particularly interesting subject. I like to start with the question, what is a statistical model? Well, you know, like all students, in front of the final exam who have no idea, will ask the wiki. Okay, so we go to the Wikipedia. And so according to Wikipedia, a statistical model in mathematical terms is frequently thought of as a parameterized set of probability distributions. So P is a probability distribution that depends on some parameter theta. So it's a set of probability distributions indexed by some set theta. Another site, planetmath.org, says a statistical model is usually parameterized by a function called a parameterization. So it's the same description. So capital theta is a parameter space, typically a subset of R to the n, that indexes some collection of probability distributions. In the statistics literature, there's actually a paper with this title a couple of years ago in the Annals of Statistics. McCulloch says this should be defined by category theory, but we're not going to do this today. You know. Instead, what we're going to do in this talk, first of all, to keep things simple, we're going to consider discrete data. This seems to have a little feedback. Maybe we should. So we're going to look at discrete data, the ones that are common in molecular biology. And we're going to suppose that the parameter space and the parameterization are described by polynomials. And this makes a lot of sense for Gaussian distributions, but I will not talk about Gaussians. I'll talk about discrete data today. So here's the picture that you should have in mind. So we're going to look at distributions on a finite state space, maybe 3 elements. So then the probability distributions on 3 states are the elements in a simplex, in a triangle, right? So the probability that you or I get picked are P1, P2, P3, non-negative real numbers that sum to 1. So that probability distribution is somewhere here. So that's that point is a distribution. And the model, a statistical model, is a family of distributions. It's going to be some subset that you can think about, you can think of as a curve, and this subset in this talk will be described by polynomials. So we're going to be in the setting of algebraic geometry. And I'm going to introduce this by way of a simple example of 3-way contingency tables. So x, y, and z are random variables. Well, x has A states, for instance 3. Y has B states, and z has C states. So now a joint probability distribution is an A by B by C table, or matrix, or tensor of numbers, non-negative real numbers that sum to 1. So think about a Rubik's Cube. So try to imagine a Rubik's Cube, you know the Rubik's Cube, that's filled with non-negative real numbers that sum to 1. So that's a distribution. So the entries represent the probabilities. So the I, J, K entry of this table is the probability that x is in state I, y is in state J, and z is in state K. And the set of all distributions forms a simplex. But now the simplex has dimension A times B times C minus 1. So now a statistical model is this red thing. It's a subset M of the simplex, which can be described by algebraic equations and inequalities in the coordinates. So according to the Wikipedia, according to the ultimate wisdom of the Wikipedia, a model comes to us by way of a polynomial map. So usually there's a low-dimensional parameter space somewhere. There's some parameter space theta, and there's a map, and then the model is actually the image of that map. And oftentimes we will be interested in taking this parametric description and finding the implicit constraints that hold in the image space. So here's the simplest of all possible models, the independence model, what probabilists and statisticians call independence, or physicists call pure states or mean fields. So I'm going to say a distribution P is independent if each probability is the product of the corresponding marginal probabilities. So if P, I, J, K factors as the product of Pi plus plus, which is the probability that X is in state I, times the probability that Y is in state J, times the probability that Z is in state K. Okay? So the event that it will rain in Aegean tomorrow, and that the Germany will be soccer world champion next year, the probability of that joint event is probably independent. So the probability of both of these things happening is the product of the respective probabilities, and that model is called the independence model. So all distributions that satisfy this are called independent. So what I've given you, according to the wiki, is a parametric representation. So the parameters of this model, alpha, beta, gamma, are simply distributions, points, in the simplices of dimension a minus 1, b minus 1, and c minus 1. And then the joint distribution is calculated by multiplying them together. So the probability of x being in state I, y, k, and z in state k is the product, alpha I, beta j, gamma k, where gamma k is some unknown parameter that says country K will win the World Cup championship next year. Okay, so that's the model. Now you can see there's a low-dimensional space mapping to a high-dimensional space, and we're interested in understanding this image. Now, this is a very, very, very well understood situation. So algebraic geometers know this image. In algebraic geometry, this is called the Segre variety. The Segre variety is the image of the product of these simplices inside the big simplex. Although what algebraic geometers do, they usually make the problem much easier by forgetting the inequalities, by replacing the real numbers with complex numbers, and by replacing affine space by projective space. So it's a time-honored tradition, 200 years old in algebraic geometry, to simplify the problem by replacing, real numbers by complex numbers and affine geometry by projective geometry. But in any case, the Segre variety, and so the points are the A by B by C matrices tables of rank 1, tensor rank 1. That's the definition of rank 1. Now, to be even more concrete, let's look at this for the case of 3 binary random variables. That A, B, and C are 2. Then the ambient simplex is going to be a 7-dimensional simplex because we have 8 states. And the parameterization that's given to us has 3 parameters, alpha, beta, and gamma. So alpha is the probability, so let's make a story, right? So you would like to know, well, anyway. So alpha is the probability that the first variable is 0, and 1 minus alpha is the probability that it's in state 1, right? They have to add up to 1. So this is the parameterization. So now you're interested maybe in the implicit constraints. So we're parameterizing a 3-dimensional subvariety, a 3-dimensional red wiggly model in the 7-dimensional simplex. So you're interested in the implicit equation. And of course, in Maple or Mathematica, you quickly run the Grobner bases. And here are the implicit constraints. So of course there's one trivial constraint that says that these 8 quantities must sum to 1, right? That's certainly true for every distribution. And then there are the quadratic constraints here. So this is a toric model. It's defined by binomial equations, and they have this form. So for instance, this times this is equal to that times that, which you can check by plugging in. Okay, so there are 9 quadratic equations, and they characterize the image. So a distribution is independent. A distribution for 3 random variables is independent if and only if these equations are satisfied. Now, what do statisticians do with their data? Well, you might have some sample, you might have some thing that you like to calculate, whether, so maybe you would like to test in a certain disease association study in genetics. You would like to know whether 3 particular loci are biased relative to the disease. So maybe you have 2 alleles in each loci 0, 1, and now you look at 1,000 people and you check, you haplotype them in that sequence. They either have a 0, 1, on the other spot they have a 0, 1, or they have a 0, 1, and then you have some empirical data, and then the data that you get from the 1,000 people, well, is here, right? So it's some particular, empirical distribution that you get here. So this is where the data come, right? So the whole point we study statistics is that we have the data here. And now your task as a statistician is to decide, does the independence model hold or not? Is it independent, right? Is, lung cancer independent from smoking a lot? Yes or no, right? So that's, that's something you need to decide based on the data that you're given. So geometrically, you need to decide whether the data are on or close to the model. You need to tell, are the data close to the model? And if you decide they're close to the model, then you need to fit, and you need to find the parameters alpha, beta, gamma. Well, of course, one way to decide whether you're close to the model is to plug in, right? So you can plug in, so you're exactly in the model if these constraints vanish, and they're approximately in the model if they approximately vanish, and that's a whole theory, and that would be a course, a year's worth of course on statistical testing. But the basic idea is you have data, and you plug in, and you decide, whether or not these things are 0. Now, so when you measure the distance, when you measure things as 0, statisticians, they have their own measure of distance. You don't usually take the Euclidean distance. You would take something called the chi-squared statistic. So statisticians have their own way, meaningful ways of measuring distance. But in any case, basically you plug in, you know whether you're close to 0. So that's the independence model, a very, very simplest model. Maybe are there any questions? Am I going too slowly? I can speed up a lot. Okay, so then let's look at some, so this is sometimes called the Markov basis. These binomial relations are called the Markov basis, and that's a popular topic nowadays at the interface of statistics and commutative algebra. I just saw one floor up, there's a commutative algebra course going on, so many commutative algebraists study these kind of relations. So these kind of Markov bases, these binomial relations, they make sense for a wide range of statistical models called log linear models. Graphical modeling in particular, very, very important in statistical learning theory. For commutative algebraists, they're minimal generators of a toric ideal, and practitioners use them to build Markov chains for sampling from conditional distributions. But most important, you can compute these kind of relations for much, much, much larger examples. If you have a much, much, much larger example, there's quite efficient software called 42 that will calculate the Markov basis of such a model for you. Of course, sometimes you don't need to do that. Sometimes you can just prove a theorem, right? So for the Segre variety, the independence model, you don't need to compute. It's very easy to prove this theorem. So if you have the independence model on 3 random variables, then the Markov basis will always consist of quadratic binomials of this form: probability times probability minus another probability times another probability. And this is the number, this expression is the number of elements you have in this Markov basis. So if you plug in A equals 2, B equals 2, and C equals 2, in this expression you get 9. And in fact, you don't need to, in general you have maybe billions and billions of these elements. You don't need to write them all down. To make efficient use of this Markov basis, you will not store them all on your computer file, but you will give a more compact symmetric representation of this that takes the structure and symmetry into consideration, and the mathematical object, mathematical theory that's used to deal with this is representations. So exploiting the symmetries and using representation theory, you can write down the Markov basis very quickly, very compactly. Okay, so that was very simple. That was the independence model. Let's move on and come to a more interesting situation. So these are mixture models. So I'm going to say a distribution P is a mixture of independent distributions if P is a convex combination. P equals lambda P prime plus 1 minus lambda P double prime, where now P prime and P double prime are independent. And lambda is between 0 and 1. The set of such mixture is called the mixture model. So the picture of this is, so here's our ambient high-dimensional probability simplex. Here's our very, very low-dimensional independence model. And maybe you have 2 independent, distributions. You have here, you have one distribution, and here you have another distribution. And maybe this is some fishery study, right? And you want to compare, some features of Korean halibut and Japanese halibut, right? So maybe they have slightly different feature, but of course, maybe here is, the Korean fish, and here is, the Japanese fish. But as you catch these fish, it's sort of hard to tell them apart, right? So really, maybe there's some independent trait, but the parameters are different. But you catch these fish, in the sea in between, it's hard to tell where they're coming from. So really, you're going to have a convex combination, of these distributions. So this will be called a mixture model, and it may or may not be so easy to decompose this mixture into the constituents, into the 2 fish populations. Okay, so back to the wiki presentation. So we're now given the first mixture model of the independence model in parametric form, right? So now we have 2 independent distributions. So to specify 2 independent distributions, we need to take our old parameter space squared, right? So we have 2 sets of parameters, alpha prime, beta prime, gamma prime for Korean fish, alpha double prime, up to gamma double prime for Japanese fish. And finally, there is a mixture parameter, which is simply in the one-dimensional simplex. It's a real number between 0 and 1. And again, we're mapping to the big simplex. Now, it turns out that the algebraic variety, the image of this map, has the expected dimension. So you can count the expected dimension. So the degrees of freedom is, well, whatever the dimension of the red variety was here for the first red point, then you have a second red point, and then you have 1 degree of freedom. So there's an obvious parameter count. So this says this mixture model has the expected dimension, and in statistics, people say the model is identifiable. So identifiable means that if you have data, and your data are on the mixture model, you can uniquely, locally, it's a locally one-to-one map, so you can locally recover the parameters by solving, solving for the parameters, solving the equations. It's an identifiable model. Now, what does this correspond to in geometry? So in algebra, well, mixtures correspond to secant lines, right? You can see you have this curve, you have this red curve, and we're drawing a secant line. So we're making the problem easier now by complexifying and passing to the Zariski closure, right? So we're going to take the line, and we take the segment, we're replacing it by the full line, and so we're getting is the first secant variety of the Segre variety. In algebra, this means we're now looking at tables of rank 2. We're looking at A by B by C matrices of tensor rank 2. Okay, so now it's a little less trivial to characterize the equations, but there is a theorem that the homogeneous prime ideal of the first mixture model, the equations that vanish on tables, matrices of rank 2, is now generated by cubic polynomials in the probability. So the original variety is defined by quadrics, and the first mixture is defined by cubics, as this gentleman well knows. So in the probabilities Pi, J, K, now there's a precise description of these cubics. They are the 3 by 3 subdeterminants of 3 ordinary matrices, and these are gotten by flattening the 3-dimensional table. So we have a 3-dimensional table of unknowns. So think about a Rubik's Cube. So you have an A by B by C Rubik's Cube, and now I'm going to take this Rubik's Cube and I can slice it this way, or that way, and I can lay it out, right? And I can lay it out as an ordinary matrix of format AB times C, or I can lay it out as a matrix AC times B, or I can lay it out as a matrix of format BC times A, and a moment's thought convinces you that the 3 by 3 minors, the 3 by 3 subdeterminants of these ordinary flat matrices must vanish on our mixture model, and the theorem says the converse is true as well. In fact, in the scheme theoretic sense, in every sense, these 3 by 3 minors generate the prime ideal. This was conjectured in 2005 with Stillman and Garcia, and it's funny actually, this paper appeared before that. Landsberg and Menivelle shortly afterwards proved it, but there is a very, very general version that appeared in a phylogenetic context motivated by evolutionary biology models in a beautiful paper by Dreisma and Kotler that appeared last year. So it's an interesting question to describe the implicit constraints that cut out the red variety, and for first mixture models this has been accomplished. Now, in general, it's quite open. Really, what we'd like to do, we'd like to understand higher tensor rank, and we're particular, an open problem is the case of 4 by 4 by 4 tensors of rank 4. Now, why is 4 important? Well, 4 is important because it's the cardinality of the set ACGT. There are 4 nucleotides, the basic building blocks of carbon-based life, and the most simple model from which all other, many other evolutionary models are derived is exactly that. It's the model of 4 by 4 by 4 tables of rank 4. And there is a conjecture what the equations are. There are certain, it's a higher secant variety, they're not just of degree 5. So there are some equations of degree 5, as this gentleman would have guessed, but there are also equations of degree 6 and of degree 9. There are lots and lots and lots of equations, but of course we have representation theory to help us. Right? The general linear group GL4 acts this way, and that way on the Rubik's Cube, the 4 by 4 by 4 Rubik's Cube. So there's a precise description, and there's a conjecture, and if you solve it, there's a problem, since I mentioned fish, so there's a problem, there's a prize on this problem by Elizabeth Ullman. She's a math biologist at the University of Alaska in Fairbanks, and people in Alaska in their spare time, they fish salmon, and so she will catch a salmon, and she will smoke it, she will package it, and she will send it to you anywhere in the world if you can prove that the tensors of rank 4, the prime ideal is generated by equations of degree 5, 6, and 9. Oh, let me make this very concrete. Let me explain these flattenings. So suppose we have, just to have a concrete example, we have one ternary variable and two binary variables. So A is 3, B and C are 2. So the theorem by Landsberg and Manivel said that the first mixture model is characterized algebraically by the vanishing of the 3 by 3 minus of this 3 by 4 matrix. There's only one flattening, right? If you have a 3 by 2 by 2 table, you can either flatten it to a 3 by 4 or to a 2 by 6. But you know, a 2 by 6 matrix, all 3 by 3 minus vanish, right? So a 2 by 6 matrix can never have rank 3. So that's it. That's all we need to know. Okay, so that's a simple example. Now, if you have these constraints, you can actually use this. So let me tell you a tiny bit more about the sociology of statistics. So in classical statistics, there are two camps. There's a frequentist statisticians and Bayesian statisticians. So in classical frequentist statistics, the way, if you have the data and you like to find, you know, the best fit on the model, you do not minimize the distance. You never minimize the Euclidean distance. What you do is you find the best fit by looking for those parameters that maximize the likelihood that you would have observed the data given the model. Right? So you're given the data and you have the model, but the model has unknown parameters. You don't know what the parameters are. For each parameter value, you can calculate the likelihood that, you know, those parameters would have produced those data. That's a number. Okay? Now, for each parameter value, you have that number, and then, you know, you maximize. So that's classical frequentist statistics, and it maximizes the likelihood. And if you have the implicit constraints, you can use that to determine likelihood inference. So the way this works, for instance, in this model, you have some data. So the data are non-negative integers, u, I, j, k. Okay? So u, I, j, k is the number of samples you've taken where the first, you know, feature is in state I, the second feature is in state j, and the last feature is in state k. Okay? So that's a Rubik's Cube full of non-negative integers. Then the likelihood up to a certain multinomial coefficient is simply this product, this monomial, and the goal is to maximize this monomial over this variety. So that's likelihood inference. So over all matrices of linearly 3 by 3 matrices of rank 2, we want to maximize this number. So we can do this exactly. You can do this exactly in Mathematica using Markov Basis or Single or Macaulay, whatever you use. And this model has degree 26. So what this means is you can write down the maximum likelihood point as an algebraic function of degree 26 in the data. Okay? So the data come in. These uij's, they are integers. You know? Now, usually people in applied field would run a numerical hill climbing algorithm, something called the EM algorithm, the expectation maximization algorithm, to numerically approximate this solution. And of course it's very hard. You're never going to be guaranteed that you're actually at the true optimum point. It's a numerical hill climbing method, right? But suppose you are, then this has some floating point coordinates, and each of these floating point numbers, in truth, is an algebraic number of degree 26. So you can, you know, study this. It's a very interesting problem to find the ML degree. It has to do with sheaves of differential forms with logarithmic poles along the divisor given by the likelihood function. So there's some nice algebraic geometry in it. But unfortunately, we can't push this very far. Again, we're very interested in the case 4 by 4, right? Because 4 happens to be the cardinality of the set ACGT. And to really push this further, we'd like to do this for larger matrices. Now, I had given there was a particular data set that I was interested in, and I offered in a course at the ETH in Zurich, I offered 100 Swiss francs for solving exactly that particular optimization problem. That became, a couple people thought about this, became known as the 100 Swiss francs problem, and and a Chinese graduate student at Clemson University collected, so he actually solved it, and that really quite gave a boost to his interest in his career. He has a very, very nice postdoc in a rather wonderful lab at Duke University. Okay, so algebraic statistics is good for something, right? It might give you fish or Swiss currency, at the very least. Now the other camp, so I said they're frequentist statisticians. So frequentist statisticians want to maximize the likelihood function. Now the other traditional camp are the so-called Bayesian statisticians. And what Bayesian statisticians do, they will not maximize the likelihood function, they will integrate the likelihood function. Okay? So the optimization problem has been replaced in Bayesian statistics by a problem of integrating. So let me explain this. So again, we have a data table, U, I, J, K. Okay? Let's do an example. So, what was A, B were 2, and C was 3. Okay, so you like to study whether, watching too much soccer on television causes loss of hair. So this was actually a study that was done in England a couple of years ago. So people study these things, okay? So you go 1,000 subjects, right? And you give these, maybe you look at 3 random variables, how many hours per week do they watch soccer? So almost never, a little bit, a lot. Okay? So that's I is 0, 1, or 2. That's I is how much soccer you watch. A J is how much hair you have, right? I mean, a lot of hair, a little bit of hair, no hair. So that's a J, is maybe between 0 and 2, And then K is gender, right? Because this is actually, this turns out, a posteriori, this turns out to be a conditional independence model. These two features, hair and our number of television hours, soccer, is actually independent given gender. So to really have the right control, you need K is 0 for male, 1 for female. So now you go out, you ask 1,000 people, and you fill in the table, right? So, so U 0, 1, 0 is the number of male people with a little bit of hair who never watch soccer. Okay? These are integers. Okay? So now, given these integers, in frequentist statistics, we want to maximize this likelihood function. In Bayesian statistics, we want to integrate it. So it's the same, Pij raised to the Uijk, but now we're going to integrate it over the space of parameters. So here we have the space of parameters, and we're going to calculate this integral. So this integral is an integral over a polytope in this example. So in this example, the parameter space is a polytope. It's a product of simplices, so it's a convex polytope. And, well, you have to specify the measure, right? So what are you going to integrate against? Well, if you've never seen this, the first temptation you might is to take just Lebesgue measure. Right? You would integrate, you just take ordinary, normalized Lebesgue measure on this polytope, and that's a good first start. But Bayesian statisticians, they specify a measure on the parameter space, and that's called the prior belief. So the prior belief is a measure on the space of parameters that quantifies what you believe, prior to having done the experiment. What's your belief about the situation, right? So you're more likely, to encounter males than females, perhaps. Or maybe, there are more people with hair than without hair, right? So you have some belief. So based on that, you believe that, alpha is more likely to be in the positive range, and beta 2 is more likely. So that's a measure on the space of parameters. And in Bayesian statistics, you integrate against the measure, and then based on that, you draw your conclusions and you update your prior belief. Now, this is fundamentally important. I mean, I would predict that 2/3 of the people at the KAIST engineering school today, in one form or another, do that. They do Bayesian inference in their algorithms. Okay? Now, we can, of course, people in practice use, numerical techniques for doing these integrals, but algebraic statistics actually can offer tools for exact symbolic integration when, the sample size is very small. Right? If the sample, the number of British people you ask is small, maybe 100, Or when U is very, very large, it can provide tools for asymptotic analysis. So for very, very large. So you can look at the asymptotics of these integrals for very, very large sample sizes. And okay, maybe a word about this. So maybe the exact integration part for small. Well, we had one project with Xiaowei Lin, who's a student, and Xicheng Xu, who was a postdoc. So for uniform priors, just for simplicity, the value of the marginal likelihood is actually a rational number. This requires a little bit of a proof. You want to actually do this integral. And if the measure is the Lebesgue measure and the U's, this is actually a rational number. That's not so hard to see. Now the difficulty is you can't do this integral, right? Because if you try to expand, if you try to multiply this out, the Uij's, they sum up to 100. You cannot, right? You're going to have 2 to the 100 terms. So the whole point is you want to do this integral exactly without expanding the product. That's the whole point. Now, what people in practice, often they don't use uniform priors. They use certain measures called Dirichlet priors. And there it's not quite a rational number. It's a special values of gamma functions. But we can get these exactly. So there's symbolic, software in Maple. They will do this for a wide range of models, such as the independence models and mixtures of independence models. So here's a simple example. So suppose this is our table. So we have 3 by 3 by 2 table of data, right? So small table. This is the flattening, right? To be in the model, you want to know, is this close to being a rank 2 model? And then, the marginal likelihood of this data, so this is this integral, is this number. So this is against uniform prior. So here the prior is, so here's the 9-dimensional parameter polytope, right? So the independence model is 4-dimensional. It's a triangle times segment, right? So the independence model is 4-dimensional. Segre variety is 4-dimensional. I take 2 copies, right? And the secant variety has the expected dimension, which is 9. Okay, so we have the 9-dimensional parameter polytope. We're integrating this monomial against the uniform measure, and there you go. There's some nice. You can do this exactly, very, very rapidly. Now I said. So this was just to illustrate a little bit the exact integration. Maybe I should also mention, since this is an audience, I think more of math students than probably of applied people. So you mentioned one other. Actually, in a week from now, I'm going to go to Tokyo, and there's a very interesting lab in engineering that's headed by a former student of Hironaka. Hironaka is a well-known algebraic geometer known for his work on resolution of singularities, and that's actually very much related. So, so these people in Japan have a theory. These are engineers, but the head of the lab studied under Hironaka. That's the point, So they have a theory that they can asymptotically, get information about this if they can only, study the singularities of these curves where they fit together. And if we had, exact resolution of singularities, we could get the asymptotics very, very accurately. So we're kind of working with them. My student Xiaowei is working with them now. So resolution of singularities in characteristic 0, well known, is implemented in Singular. Right? You know that you can run resolution of singularities on your laptop, right, using the software Singular. The trouble is it's very, very slow. And it really doesn't work on any practical problem. Not so much because the algorithm is slow, but because the output is too large. If you actually want to do resolution of singularities for an applied problem in practice, in any problem, the software will produce charts and charts and charts, billions of charts. Right? So the whole problem with resolution of singularity algorithms is that the output size is astronomically large. It's not that the running time is slow, it's the output size is very, very large. So what we need to develop as algebraic geometers who want to contribute to engineering is we need to develop tools for doing resolution of singularities in a much more sort of precise way, that we, without producing billions and billions of charts, that we can answer questions about the singularities without going to a full resolution. So the key ingredient is a real version of the theory of multiplier ideals. I'm not going to say more about this, but this is again a kind of a hot topic in the interface of commutative algebra and algebraic geometry, which for me, as always, is part of applied graph. Okay, so much about Bayesian inference. Let me talk a little bit more. Maybe are there questions? Maybe I should pause. Just realized I'm being filmed, you know, and all these strong opinions about resolution and so on. That's okay. Okay, so let me talk for the next 10 minutes, 5 to 10 minutes, about another model. These models are, for practitioners, they're very, very simple. You know, these independence models and mixtures of independence models, they're very, very simple. Let me just give you just a small variation, something that I looked at, you know. Of course, the higher mixture models, right? So higher mixture models, you mix R independent distributions. Here I wrote the same thing in tensor notation. So higher mixture models are secant varieties of Segre varieties. They correspond to tables, you know, Rubik's cubes that can be written as the sum of R independent models, R independent tables. And again, for R equals 4, you know, you can win Alaskan salmon. You can write down the ideal. But let's vary this a little bit. Let's look at a certain submodel. So what happens when you form these higher models? The dimension gets very, very large. And statisticians don't like that. So from the point of the statistician, well, you don't know the model, right? You're given the data. Right? All you're given is the data. Now, of course, you know, you can always find some model that going to fit all the data, right? So take as the model the entire simplex. If you take a very, very, very large dimensional model, then of course, you know, you're going to fit the data very, very well. So the secret is you don't want high dimensional models, you want low dimensional models. You don't want to overfit the data, right? So the simplex is very, very large. But the red wiggle, the statistical model, you want it to be very, very small, to have a meaningful interpretation. You don't want many parameters, you know, you want to have few parameters, right? You want to have a simple explanation. Okay, so these are called context-specific independence models. We looked at this when I was in sabbatical with, again, a computational biologist from Max Planck Institute in Berlin, Alexander Schliep, and his student. So the paper is from bioinformatics called Context-Specific Independence Mixture for Positional Weight Matrices. And the biological problem was to study transcription factor binding sites on some genome. Anyway, so here's the math. So a context-specific independence model is specified by 3 partitions. So A, B, and C are partitions of 1 up to R, set partitions of 1 up to R. So there are bell many of these, okay? So we take alpha, beta, gamma, A, B, C are set partitions of R. Remember, R is the rank, the number of summits. Now these partitions, they describe how the parameters are tied together. Okay? Namely, the parameter AI, so this is, you know, the how much soccer you watch parameter, and this is the, you know, this is whatever, is the boldness parameter, and this is some gender parameter. These are some, they have a meaning. Each of these has a meaning. And the rule is that AI should be equal to AJ if I and J, the states I and J, are in the same block in the partition A. Right? So that's a very, very meaningful thing in this kind of, in these kind of situations, particularly in this, where this came from, this was very meaningful. So likewise for B and for C. So the vector, the parameter vector Ci is said to be equal to the parameter Cj if I and J are in the same block in C. So this cuts down the number of parameters by a lot, depending how you choose these partitions. So it's kind of an open problem to study these, you know. So there's a a whole, I don't know. So we started this, then my collaborator got a little sick, so I would love, if one of you, with the background in commutative algebra or algebraic geometry just jumped on this. And the first question is, what's the dimension, what's the singularities, any question you can ask about these. But let me just show you, just to tease you, right? Let me show you one example, show you that this is actually interesting. So let's say R is 3, and let's fix 3 set partitions. So the first one is just the 1 and 2 is together with 3, and then B is 1 is 3 is together with 2, and C is 2 and 3 is together with 1, right? So what's the story, right? Let's say there's a presidential election and 3 candidates run, McCain, Clinton, and Obama, or something, right? You have 3 candidates running for president, and then maybe you have 3 issues, right? So the issue is I don't know, should you, some political issues, right? So A, B, and C. And on issue A, well, the supporters of McCain and Hillary are likely to have the same opinion, and the third is different, right? And then on issue B, it's the first and the third. That's the that's the model you want to test, right? You have some issues, R, political issues. R equals 3. Should you go for war in Iraq or something, right? And then there are 3 candidates, and then the supporters will have the same or different opinions. So that depends. That's an example of a context-specific model. Now, in terms of the parameterization, so pi j k is lambda alpha I beta j phi k plus mu alpha I. So now you can see, you see this alpha I is equal to that alpha I. Right? So this is the parametric representation of the model, or in multilinear algebra notation, the tensor P is a rank 3 tensor. It's a sum of 3 independence tensors, but these are the constraints. I'm tying this together. So the question is, which 3-dimensional tensors can be written like that? That's the multilinear algebra question. Okay, so here's the answer. So it turns out, so this particular small example, this particular CSI model, context-specific independence model, is the so-called tangential variety of the Segre variety. So it's the set of all points. So I talked about secant variety earlier, but you can also pass to the limit, right? So that's what we do in calculus. So in calculus, we have little curves like this, and then we have tangents, but then in the limit, we have secants, but the limit, of a secant is a tangent. And those are the ones we study in calculus. So the tangential variety is the set of all points that lie on a tangent to the given variety. So that's the CSI model. And this particular example is the tangential variety of the Segre variety. And, well, you can calculate the homogeneous prime ideal. It's quite nice. It's generated by the 2 by 2 by 2 hyperdeterminants inside the A by B by C Rubik's cube. Well, together with the minors coming from flattening, right? So certainly we have to have the old relations, the 3 by 3 determinants that we had from flattening. That's just saying that you're in the model at all. And then together with that, and I think that's actually a typo. I think this should be 4 by 4 because we have 3 summits. But in addition, the new equations you get are the 2 by 2 by 2 hyperdeterminants. And well, the students in the room, you may not have looked, so you're all familiar with the ordinary determinant of a 2 by 2 matrix, right? That goes A times B minus C times C. But if you have a 3-dimensional matrix, a 2 by 2 by 2 matrix, there's also a notion of determinant. The hyperdeterminant goes back to Cayley, 150 years. And here's the formula. So, oops, sorry. There we go. So here's the small example. So if we take A again to be 3, B is 2, and C is 2, and we take the CSI model, the Obama, Clinton, McCain model. This red model is an 8-dimensional model. It lives in an 11-dimensional simplex. The degree of the projective variety is 16. But now the model is not identifiable. The dimension of the model is smaller than the number of parameters. That's typical for these models. And the ideal is generated by the 4 3x3 subdeterminants of the flattened matrix and 6 2x2 hyperdeterminants, and they look like this. So this is the determinant of a 2x2x2 matrix, the so-called hyperdeterminants. Physicists call this the tangle. The tangle, this is the entanglement measure for a 3-qubit system. So when I say a 2x2x2 matrix, a physicist would call that a 3-qubit system. And this polynomial to vanish, or the further it's away from 0 in absolute value, the more entangled the 3-qubit system is. Now, there are 6 of these hyperdeterminants. Why are there 6? Well, think about it, you know. We have a 2x2x3 table. How many 2x2x2 blocks can you fit in there? Well, looks like you can only fit 3, right? Let me draw this. So you have a block like this. So these are our tables. And we're interested in the hyperdeterminantal ideal of all 2x2x2 blocks. 2x2x2 blocks that sit inside. But looks like if there's only 3. It looks like there's only 3. But that's actually a fallacy because there's a group action. Yes, you have the general linear group acting this way, and that way. And for the high dimensional table, there's actually more. There's an additional symmetry. There are actually 6. So after you make a change of a basis, there are actually 6 2x2x2 blocks sitting inside a 2x2x3 table. And this is the hyperdeterminant. So this was just a tiny example. So as I said, this is a wide open field. Poor Alexander Schlieb got a little sick, hopefully not from working with me, but he also is very busy with the biology problems, but this would be a great model for students to try themselves on. That's the end of the talk. So here's the conclusion. Algebraic statistics has 2 important features. First of all, the feature for pure mathematicians, it's actually cool, you know. Statistics is much more cool than you think. Most math students, when they're forced to take one statistics course as undergrads, they hate it, right? Because it's boring, it makes no sense, you know. Besides, it's for the stupid kids, right? The smart kids take number theory, and the stupid kids take statistics. Well, I got a surprise for you. If you're smart enough, you know, to take number theory, you should really, really try to understand statistics at a deeper level. It's really, and you'll find it cool. Now, the message for the applied people, you know, the 2/3 of the KAIST faculty engineering, algebraic methods are more useful than you might think. Of course, I'm not claiming, you know, I'm not selling snake oil. I'm not claiming that Grobner Basis, you know, can solve large models exactly. What I'm saying is it can solve small models exactly, and it can give a very, very precise insight that practitioners and numerical people can then use to test, you know, large-scale models and large-scale numerical algorithms against the predictions coming from small, precise calculations. And of course, you know, I've got a book to sell, right? So if you want to read more, you know, Matthias Dotton, he is a faculty member in the statistics department at the University of Chicago. Seth Sullivan is at North Carolina, and we gave an Oberwolfach course last year, and the book just appeared. It's called Lectures in Algebraic Statistics. Thanks for your attention.